Welcome to my introductory video on energy. Hopefully you've read the first couple pages of the notes before you've approached this video. If not, that's okay. The understanding of energy can be quite an abstract concept. In this unit, you'll be introduced to many different energy terms such as um, kinetic energy, rotational and translational, or mechanical energy, uh, potential energy, gravitational, elastic, chemical energy, nuclear energy, all these different types of internal energies. And then you have concepts of like conservation of energy or the work energy theorem. And so when you're approaching the mathematics, it can be quite confusing. So what I would say that you should strive to do is to spend time at the beginning of this unit to really understand the words and the concepts, and then later associate them to the appropriate symbols and equations. And then when you get to the mathematics, it'll be much easier. So let's first start off with the basic energy model. If you could flip to page 3 in your notes, and over here you'll see a picture shown on the upper right corner of, of a system. Now the system is defined by this red barrier that goes around here, which is the boundary between the system and what's outside of it, which we call the environment. A system, by the way, is just a collection of one or two or more objects. Kind of like if you look at this picture down below, you have a weightlifter who is converting chemical energy stored in her body to gravitational energy. Well, the system in this case would probably include the barbell and her and even the ground that she's on top of. So that would be our system. Um, we've already actually discussed systems before when we talked about forces. Maybe this might help you to understand them. Let's take, for example, you have a situation where you have two billiard balls, like say billiard ball A, which is moving along here to the right, and then here you have billiard ball B, maybe it's just standing still. And then suddenly the two billiard balls A and B basically collide with each other. And when they collide, there would be a force of A exerted on B, and there would be a force of B exerting a force back onto A. And if you recall Newton's laws, there is a third law that talks about every action force will have an equal and opposite reaction force. So the force of A onto B would be equal to the force of B back onto A. Now we talked about systems when we looked at that, and we might define a system to be A and B completely together. And because things got a little bit confusing, we typically use this kind of dashed line around the system of objects to represent the system. And in this particular case, then these two forces, A onto B and B onto A, would be then considered what we call internal forces, and they would cancel out. And so then we would realize that really the net force is zero. Okay, hopefully you now get the idea of how we can designate a system by pointing out one or two or more objects, and how that actually could be helpful with our concepts. In terms of energy, designating a system allows us to classify which energies are internal, in here, and which ones are external, which are outside in the environment. Within the system, you can have energy that is transferred from one form, say over here, which we call kinetic, to say chemical energy, into another form or potential. So it can transfer from one form to another form within the system. However, energy can be transferred between the system and the environment. And there are three modes that can occur. One would be heating, right? And that would be because there would be a temperature difference between what's inside and outside. Say it's hotter on the outside than it is inside, which is colder, and then heat would flow into the system. You could also have radiation by photons or electromagnetic waves. And you could have work that is being done, say, on the system. And in those three modes, you could have energy that is being transferred between the environment and the system. Now, in AP Physics 1, we are only really studying the transfer of energy between the system and the environment by basically only work. Um, which is done by external forces. The concepts of heat and radiation are discussed in AP Physics 2, and that's done in the thermodynamics unit. So don't worry about that unless you're taking AP Physics 2 later on, and that's done in AP Physics 2. So we will be studying energy transfers between different forms within the system. And we will be studying how that also how the energy transfers in and out of the system by doing work. Now let's discuss the energy that is stored within the system and how it flows or transfers within that system. Now, within the system, we could call that energy, all of these energies, really just internal energy. The internal energy is a property of the system due to the microscopic energies of the particles within the system. So if you think of this particular body, we have all these molecules or atoms that have energy associated with them. There are a variety of mechanisms that internal energies transfer, say, from one form to another. So we have potential energy, which is associated, it's like a stored energy, really, and that is associated to gravitational and electric fields. We have elastic and chemical energies, which are stored within the electric fields. There are also kinetic energies, which are due to particles either vibrating or moving within the system. The thermal energies are a result of the frictional effects, which I've called the dissipated energy in here. Some folks will call this dissipated energy thermal energy, while others may simply refer to it as dissipated energy. It is important to realize that the thermal energy doesn't come from, say, heating from the environment to the system. The temperature of the system, say, would rise because of frictional effects within the system, and then suddenly the system gets warmer internally within that system. Okay, let's quickly introduce some of the different sources of energy. So within a system, we can have many kinds of energies. Let's take a look at that. Number one, let's talk about kinetic energy. The kinetic energy is essentially energy due to motion. And really, there are a variety of forms of kinetic energy. We have translational kinetic energy, which is basically energy when from an object that moves, say, from one location to another location. We have rotational kinetic energy, which is the energy associated to an object when it's rotating or spinning about some axes. And we also have, say, vibrational kinetic energy if you think of the molecules that are vibrating. Now, in terms of our studies in AP Physics 1, we'll be really only looking at translational kinetic energy and rotational kinetic energy. And all of them together, you could just simply just call kinetic energy represented with a K. We also have gravitational potential energy, which is the energy that is associated with gravity, shown in here. We also have elastic or spring potential energy, which is the energy stored in a spring-like object because it's getting deformed. So that would be energy that's in a spring or elastic band or rubber ball when it compresses against the ground. And we have dissipated energy, which I've already discussed earlier in this video. Some of this internal energy within the system might be tied up in the internal structure of the system, and it's unusable. This is energy basically that's dissipated due to frictional forces within the system. We have chemical energy, which is energy stored within the bonds of the molecules within a system. The energy transfers that occur basically from chemical reactions. So examples of chemical stored energies would be found in batteries, biomass, petroleum, gas. All right. And we have nuclear energy, which is energy that is stored within the nucleus of an atom. This is the energy that basically holds the nucleus together. And lastly, which is not listed here, we have a number of miscellaneous internal energies that encompass the changes from emission or absorption of sound or radiation or any other kind of messy interactions. Sometimes I just like to call them dissipated energy. Together, all of these different forms of energy make up the total energy, which I represent with a capital E. All right. There's a variety of ways to symbolize them. You could use a K for kinetic energy. Some people use KE, or some people use E sub K. So you might see something like that in our modeling curriculum worksheets that I've been using. Gravitational energy is represented with U sub G in the AP formula sheet. If you look at the modeling sheets, it just use E sub G. Um, Elastic potential energy in the AP curriculum formula sheet is U sub S, but if you look at the modeling curriculum, it's E sub EL. Dissipated energy is E dis, but sometimes what we've done is some people will prefer to write it as ETH for thermal energy. We have E chemical energy and E nuclear energy. And lastly, I'd just like to say that this total energy within the system stays constant if the system is said to be isolated. If you look at the top of page 4 notes, you'll see I talk about the isolated or closed system. And a closed or isolated system is a system where there is no energy transfers that go in or out of the system. So we're essentially saying that this border here, this boundary, all of the energies that's contained within this boundary stays inside. And if it stays inside and none of it can go in or out, then we could say that this system is closed or isolated. A system that is not closed or isolated would be called an open system. And we will discuss open systems, which allow energy to go transferred between the surroundings in the system when we talk about work.